Hey guys, so this is Isabella Engelman. I'll be doing Math 133, Chapter 5, Section 2, Video Assignment 1. So in Video Assignment 1, we are prompted with two questions that we need to solve for. The first one is, find the volume of the solid of revolution obtained by rotating the region by the curves y equals x and y equals the square root of x about y equals 1. The second one prompts us with a true or false, where every volume of the solid can be computed as a volume of a solid revolution. If false, show an example of a solid which is not computed as a solid of revolution. I will first be addressing the first question, and you will see me solve this in the next slide. So just a little recap on the first question for video assignment 1 is find the volume of the solid of revolution obtained by rotating the region by the curves y equals x and y equals the square root of x about y equals 1. As you can see, y equals 1 is in the graph. To know the rotation, basically, if you look at the first graph. So what I did, basically, is I plugged in 0 for my x, and then I plugged in 0 for my y equals x into x, and then y equals the square root of x, I plugged in 0 as well. As you can see, the output for A was 0. This is how we found A. And then for B, we did the same thing for 1, where I plugged in 1 for x, y equals 1, and then y equals the square root of 1. And again, the output came out as 1. I then plugged in 2, and this time I got a different answer for my y equals the square root of x, which we plugged in 2 for x, so it's y equals the square root of 2. And so basically this was a different number when we went to plot it, so therefore we knew that A and B were the equations were basically we could find where it intersects to find the shaded region in which we are looking for. So after I have graphed both equations and made a table, the second step we need to do is find the outer and inner radiuses equation in respect to the rotation y equals 1, of course. The outer radius would be y equals x equation because it's the farther outer equation from the rotation y equals 1. An inner radius would be y equals the square root of x equation because it's the closer equation from the rotation y equals 1. Therefore, we're left with our outer radius 1 minus x and our inner radius 1 minus the square root of x. Okay, so now that we have both our inner and outer radius with our points A and B, we can now write our expression to find the volume. So this is written above C. This expression is going to be our outer radius minus our inner radius times pi, all squared. So basically what I did is I plugged in for my outer radius my 1 minus x squared minus my inner radius, which is going to be 1 minus the square root of x squared. This should allow us to find our volume. Okay, so now what I did for the second step basically to this is I took the outer and inner radius and I basically FOILed out both of them to get a different polynomial equations, and this allowed me to replace them back into the expression equation that we originally wrote to find volume. So this can be done under letter C, where I took 1 minus x squared and I FOILed that basically into finding my x squared minus 2x plus 1. This was the same thing done with my 1 minus the square root of x squared, where I FOILed that out and I got x minus 2 square root of x plus 1. I then plugged both in my polynomial equations that I got from FOILing. I plugged those back into my original expression to find volume, which is seen above C. So now if we look above letter E, we can see that I took the integral or antiderivative of the expression and the equations above that I basically substituted in. This is going to be a step-by-step process basically of just showing how I did this. This is all shown above, again, letter E, so you can see that I took the integral and antiderivative of these expressions to find our volume. So now that we have the kind of the final expression, which is going to be the last line above letter E, I took that expression and I basically plugged in the values of x equals 1 and x equals 0 to find common denominators and ultimately simplify this to where I got pi over 6, not forgetting the pi at the end, of course. So how I did this is if you want to see the first line, which is going to be below letter E, above F, I took 1/3 and I plugged in my 1 into my x, and I did this again for my kind of second part that I'm minusing, my second equation that I simplified basically into a polynomial. Then I took the antiderivative. I plugged in 1 into x for that, and then I minus them again with the same concept, but instead I plugged in 0 in for x, and this allowed me to get pi over 6 because this is all being times by pi. So this was my final volume. So this is the second part to video assignment 1. This is the true or false question. Just for a recap, every volume of the solid can be computed as a volume of a solid revolution. If false, show an example of a solid which is not computed as a solid of revolution. So this ended up being false, where every volume of the solid cannot be computed as a volume of a solid revolution because, let's take a cube for example. If we try to calculate the volume of the solid of revolution, it would be impossible because with the volume of solid revolution formula, also method, it deals with x and y, but with a cube. Another variable is added and in result with a cube having x, y, and z, you wouldn't be able to calculate the volume of this solid using volume of solid revolution formula. Therefore, this remains false.